Have you ever wondered how raw iron ore transforms into the steel that builds skyscrapers, bridges, and machines? From electric arc furnaces to continuous casting and precision rolling, modern steelmaking combines powerful technology and advanced engineering to shape the backbone of our world. A blast furnace is a large metallurgical reactor used to produce pig iron from iron ore. It operates as a tall, vertical shaft, lined with heat-resistant bricks. Inside the furnace, layers of iron ore, coke, and limestone are continuously charged from the top. Hot air is blown through tuyères at the bottom, creating intense combustion and high temperatures. The chemical reactions reduce the ore into molten iron, while impurities form liquid slag. During tapping, the molten metal flows out through the tap hole. This process remains essential for steelmaking industries worldwide. An electric arc furnace, or EAF, is a powerful industrial installation designed to produce steel by melting scrap metal through intense electrical energy. The furnace operates by generating high-temperature electric arcs between graphite electrodes and the metallic charge placed inside a refractory-lined vessel. When the electrodes are lowered, electric current flows and creates arcs that heat the material to temperatures above 1600 degrees Celsius. Modern furnaces are equipped with control systems that regulate power input, electrode movement, and oxygen injection to optimize efficiency. Scrap steel, pig iron, and alloying elements are carefully charged into the furnace according to required chemical composition. During the process, impurities are removed through slag formation, while samples are taken to monitor quality. After complete melting and refining, the molten steel is tapped into ladles for further treatment or continuous casting. The electric arc furnace offers flexibility, fast cycles, efficient recycling, and sustainable steel manufacturing worldwide. Before use, the tested lance is ignited with a natural gas acetylene oxygen burner, using liquid slag at the burning point or, as shown, in a coke fire. In this example, the oxygen supply is regulated through the lance holder. The operation can therefore be carried out by only one worker. During the burning free of the ladle slide gate, there is a risk of backfire, so the oxygen valve must be fully opened only after the breakthrough is achieved. When opening the slide gate at the continuous casting plant, increased danger exists from steel splashes and intense radiant heat. Emergency ladle must be ready. Metal scrap is first delivered to the plant by heavy trucks arriving continuously throughout the day. Each truck is weighed and directed to the designated unloading area. The scrap is then tipped onto the storage yard, where it is sorted and organized according to type and size. Large handling equipment gathers the scrap and transfers it to charging baskets. These baskets are carefully loaded and transported to the melting furnace. Once positioned above the furnace, the scrap is charged inside in controlled batches to ensure stable melting conditions and efficient heat distribution. Inside the high-temperature furnace, the metal scrap is subjected to intense heat until it melts completely. Powerful burners and controlled oxygen injection accelerate the melting process while ensuring uniform temperature throughout the molten bath. Impurities rise to the surface and are removed as slag. Chemical composition is adjusted by adding alloying elements to meet required steel grades. Samples are periodically taken and analyzed to confirm that the molten steel meets precise specifications before tapping. When the melting process is complete and the composition is verified, the liquid steel is tapped from the furnace into a ladle. The ladle transports the molten steel to the casting section. From there, the steel is transferred into the tundish of the continuous casting machine. The plant operates a 5-strand continuous casting machine, CCM, enabling simultaneous production on 5 casting lines. The machine applies the submerged casting method, where molten steel flows through water-cooled molds. As the steel enters the square mold, it begins to solidify from the outer shell inward while remaining molten at the core. The partially solidified strand exits the mold and continues through a series of secondary cooling zones. Water sprays control the cooling rate, ensuring internal structure consistency and preventing cracks. Gradually, the strand solidifies completely into square billets. These billets are continuously withdrawn by rollers and cut to predetermined lengths using automatic cutting systems. Each billet is then transferred onto cooling beds, where it reaches a uniform temperature suitable for the next processing stage. After cooling, the square billets are transported to the rolling mill for hot rolling. In the rolling section, the billets are reheated in a furnace to achieve the required rolling temperature. Once the target temperature is reached, the billets are discharged and fed into a sequence of rolling stands. Each stand progressively reduces the cross-section and elongates the billet. Through repeated passes between rotating rolls, the material transforms into long steel bars with controlled dimensions. The hot-rolled steel then undergoes controlled cooling at lower temperatures. This stage enhances mechanical strength and refines the surface finish. By adjusting the cooling rate, the internal grain structure is optimized to improve durability and performance. The bars are straightened and cut to standard commercial lengths. Surface scale formed during hot rolling is minimized, and the finished bars display improved dimensional accuracy and surface quality. Following primary rolling, the steel bars are transported to another facility for further processing stages. At this plant, the bars are reheated once more to prepare them for additional rolling operations. The reheated bars enter rolling mills again, where they are reduced further to produce longer and more slender steel products. Each rolling pass carefully shapes the steel while maintaining consistent mechanical properties. After the secondary rolling process, the steel products undergo heat treatment. Controlled heating and cooling cycles are applied to achieve the desired balance of strength, toughness, and flexibility. Depending on the product specification, the heat treatment may involve normalization, quenching, or tempering. Temperature and time parameters are closely monitored to ensure uniform properties throughout the entire length of each bar. Once heat treatment is complete, the steel bars proceed to final machining processes. Surface finishing operations remove minor imperfections and ensure dimensional precision. The products are aligned and prepared for quality inspection. At this stage, the bars pass through an automatic ultrasonic testing line. This system scans each bar along its full length to detect internal defects, such as cracks, inclusions, or voids. High-frequency sound waves penetrate the steel, and reflected signals are analyzed automatically. Any defective material is identified and separated to maintain strict quality standards. After ultrasonic inspection, the approved steel bars move to mechanical processing stations. Here, they are cut to required lengths using precision cutting machines. If necessary, bending machines shape the bars according to customer specifications. Drilling machines create holes or connection points where required. Additional machining operations are carried out to meet detailed design requirements. Throughout these processes, dimensional tolerances are carefully controlled to ensure consistency and accuracy. When all machining operations are completed, the finished steel bars are cleaned and prepared for final handling. They are stacked systematically according to size and specification. Identification markings are applied to each bundle, including grade, dimensions, and batch information for traceability. The bundles are securely strapped to maintain stability during transportation. Finally, the finished products are moved to the storage and shipping area. They are organized in the warehouse while awaiting export. Logistics teams coordinate loading schedules to ensure efficient dispatch. The steel bars are carefully loaded onto transport vehicles, ready to be delivered to customers for use in construction, infrastructure, and industrial applications. Through each stage, from scrap delivery and melting to casting, rolling, heat treatment, inspection, machining, and final shipment, the process ensures consistent quality, structural integrity, and reliable performance of the finished steel products. The production process begins at the port, where an excavator with a grab attachment lifts and loads metal scrap from ships into waiting trucks. The trucks then transport the scrap metal to the steel plant. After arriving at the facility, the trucks unload the scrap into the storage yard, where it is prepared for melting. Next, the scrap metal is charged into a high-temperature furnace. Inside the furnace, the material is heated intensely until it completely melts and turns into liquid metal. Once the metal reaches the required temperature and composition, the molten steel is tapped from the furnace and poured into molds. After that, the liquid steel passes through a continuous casting machine, where it is formed into square billets. These billets are then transferred to the rolling mill and processed into long steel bars. While still red hot, the steel bars are cut into standard lengths. The hot-rolled steel is subsequently treated at lower temperatures to improve its strength and enhance the surface quality. Each steel bar is then individually marked by workers, and labels are attached to identify each production batch. Finally, the steel bars are transported to another plant for further processing. There, they are reheated and rolled again into smaller diameter bars. After the final shaping process, the finished steel bars are bundled together, completing the manufacturing sequence. The steel produced at voestalpine Donawitz represents products that can be found everywhere in everyday life, especially where exceptional performance is required. Strength, precision, and reliability guarantee a decisive step ahead. The production process begins with iron making in the blast furnace, followed by the LD basic oxygen process, where high-purity steel is created. From the very beginning, quality is the clear priority. Speed and safety, especially in modern railway systems, demand materials that make no compromise between performance and comfort. One outstanding example is the production of ultra-long rails. Thanks to an optimized casting format in Donawitz, rails up to 120 meters can be produced in a single cast. Short transport routes and reduced throughput times ensure flexibility and true just-in-time production. This efficiency makes voestalpine a dynamic and reliable partner for customers worldwide. High-tech steel quality does not happen by chance. Advanced vacuum treatment facilities reduce gas content, particularly hydrogen, to extremely low levels. This guarantees rails capable of withstanding the highest mechanical stresses. In demanding applications such as deep drilling projects reaching 700 meters, material reliability is essential. Every year, around 500 different steel grades are produced in Donowitz. Each grade is precisely defined through chemical analysis and exceptional purity. The heart of this excellence lies in secondary metallurgy, where composition and properties are refined to perfection. In the automotive sector, safety depends on these decisive steps in steel production. Low sulfur content and optimized processing characteristics provide manufacturers with superior performance and reliability. Through coordinated production routes, continuous investment, and technological expertise, voestalpine Donowitz delivers steel that sets new standards, ensuring customers remain always one step ahead. The Green Anode plant paste line of Busk Chemtech AG is a fully automated and high-tech facility designed for efficient anode production. Raw materials are transported by rail, with carbon pitch delivered in heated tank wagons and pumped into storage tanks, while petroleum coke is unloaded into hoppers and conveyed for processing. Moist coke is dried, stored in silos, and fractioned to achieve the required granulometry, with coarse particles milled further. Through intelligent recipe control, liquid pitch and coke are precisely dosed into the Busk Chemtech paste kneader, where they are mixed at around 180 degrees Celsius to form a homogeneous paste. The paste is cooled and hydraulically pressed into green anodes, then transferred through a cooling tunnel before storage. The Mega 1600th Avenue is a high-capacity hydraulic press, specifically designed for the production of green anodes, which are essential consumable components in the aluminum smelting process. Green anodes are made from a mixture of calcined petroleum coke and coal tar pitch, and their quality directly affects the efficiency and stability of aluminum electrolysis. The Mega 1600th Avenue ensures precision, consistency, and high productivity throughout the entire manufacturing cycle. The production process begins with the dosing stage. In this step, a precisely measured quantity of hot carbon paste is prepared. The paste consists of carefully proportioned raw materials that have been mixed and heated to achieve the correct plasticity. Accurate dosing is extremely important because it determines the final weight, density, and mechanical strength of the green anode. The automated control system of the Mega 1600th Avenue guarantees that each cycle starts with the exact required amount of material, ensuring uniformity from one anode to the next. After dosing, the process continues with material transfer. The prepared carbon paste is transported from the mixing system to the press feeding unit. During this stage, maintaining the correct temperature is crucial. The paste must remain sufficiently hot and workable so that it can be compacted effectively. Efficient transfer systems minimize heat loss and prevent segregation of materials, preserving the homogeneity of the mixture before pressing. Next, the carbon paste enters the filling box, a chamber located above the mold. In the box-filled stage, the material accumulates inside this chamber. The system ensures that the filling box is completely and evenly loaded. This step is essential because an incomplete or uneven fill could result in density variations or structural weaknesses in the final product. Once the filling box is ready, the process moves to the mold-filled stage. The carbon paste is discharged into the mold cavity, which defines the final shape and dimensions of the green anode. The Mega 1600th Avenue then applies powerful hydraulic pressure to compact the material. This high-pressure compaction removes air voids, increases density, and forms a solid, dimensionally accurate anode block. The pressing force is carefully controlled to achieve optimal mechanical properties while maintaining surface quality. After compaction, the newly formed green anode remains inside the mold. The anode eject phase begins when a hydraulic mechanism carefully pushes the anode out of the mold cavity. Since the anode is still in its unfired state, it must be handled with precision to prevent cracks or surface damage. Following ejection, the anode push-off system transfers the anode from the press table onto a conveyor or transport platform. This automated movement ensures smooth handling and reduces the need for manual intervention. The green anode is then transported to subsequent cooling and baking stages, where it will be hardened and prepared for use in electrolytic cells. Finally, once the anode has been removed, the mold is ready to be filled again, and the production cycle restarts. Through continuous automated operation, the Mega 1600th Avenue delivers high productivity, consistent quality, and reliable performance, making it a vital machine in modern aluminum manufacturing plants. The production of steel cages is presented as a precise and highly automated process designed for strength and efficiency. The process begins with high-quality steel bars delivered to the workshop. These bars are carefully measured, straightened, and cut to the required lengths using advanced cutting machines. Accuracy at this stage ensures that every component fits perfectly in the final cage structure. Next, the steel bars are bent into specific shapes according to engineering drawings. Automated bending machines guarantee uniform angles and consistent dimensions, which are essential for reinforced concrete applications. After preparation, the bars are assembled into steel cages. Skilled workers position the longitudinal bars and connect them with stirrups or spiral reinforcements. Welding or tying techniques are used to secure each joint firmly. Finally, every steel cage undergoes quality inspection to ensure structural stability and compliance with construction standards before being transported to construction sites. The video demonstrates the cutting and notching process of a massive HEM 800 steel beam using the advanced Kaltenbach KC1201 system. This high-performance machine is equipped with a KUKA robotic arm and a Zinsser oxy-fuel cutting torch, enabling precise thermal cutting on heavy structural steel components. First, the M800 beam is positioned securely on the machine bed. Due to its large size and weight, accurate clamping and alignment are essential to guarantee dimensional precision throughout the operation. Once the beam is fixed in place, the automated system begins the cutting cycle. The KUKA robot guides the Zinsser oxy-fuel torch smoothly along the programmed cutting path. A controlled mixture of oxygen and fuel gas produces a high-temperature flame, capable of penetrating the thick steel section. As the flame heats the steel to ignition temperature, a stream of pure oxygen is released, initiating the oxidation reaction that removes molten metal from the cut zone. This process allows the machine to create clean and accurate longitudinal cuts along the beam. The automation ensures consistent cutting speed, stable flame control, and optimal edge quality, even when working with the substantial thickness of a HEM 800 profile. During this stage, the beam is not only cut, but also notched according to the required structural design. The robotic control system precisely follows the programmed geometry, allowing complex contours and recesses to be formed directly into the steel flange and web. This level of precision reduces the need for secondary machining and guarantees that each component meets the required specifications. After the flame cutting operation is completed, the beam remains connected at specific cutting bridges. These small, uncut sections temporarily hold the parts together to maintain stability and prevent uncontrolled separation. In the following step, the steel beam is carefully separated at these cutting bridges. The remaining connections are removed, allowing the individual sections to be detached safely and efficiently. As a result of this process, a single steel beam is transformed into 3 separate T-shaped components. Each T-section is produced with accurate dimensions and clean-cut surfaces, ready for further fabrication or assembly in structural applications. The combination of the Kaltenbach KC1201 machine, the KUKA robotic system, and the Zinsser oxy-fuel torch ensures high productivity, precision, and reliability in heavy steel processing. This integrated cutting technology significantly enhances efficiency in modern steel fabrication workshops. Plasma cutting is an advanced thermal process used to cut metal with high precision and speed. In this operation, a 3 mm thick steel sheet is automatically cut using a CNC plasma cutting system. The machine applied in this process is the RUR 3500 inches thermal cutting machine, designed for oxy-fuel, conventional plasma, and high-definition plasma cutting. The RUR 3500 is built with a fully welded machine frame, ensuring high structural rigidity and stability during operation. Its beam is completely welded without bolted joints, which increases durability and minimizes vibration. The machine is equipped with a digitally synchronized twin-side motion control system installed on both longitudinal rails. This guarantees smooth and precise movement along the cutting axis. In the cross-axis, linear bearings provide accurate guidance, while the new AC servo drive system allows cutting speeds up to 12,000 mm per minute. Digital synchronization in the longitudinal axis ensures balanced motion on both sides of the gantry. The system is controlled by the new Pierce 15-inch touchscreen control panel, offering user-friendly operation and precise parameter adjustment. During plasma cutting, the torch automatically senses the initial height of the steel plate. Arc voltage height control continuously adjusts the torch position to maintain optimal cutting distance. Electric ignition initiates the plasma arc, which generates extremely high temperatures to melt the metal. The molten material is then blown away by high-velocity gas, creating a clean and narrow cut. Floating cutting heads enhance accuracy when cutting uneven surfaces. Limit switch protection in each axis ensures operational safety. The machine also allows parking of one cutting head outside the working area, when not in use. Optional equipment further improves performance. A 19-inch control system, higher speed servo drives up to 20,000 mm per minute, automatic gas console, anti-collision system, and plasma systems according to customer requirements can be integrated. Additional features such as pneumatic or plasma marking devices and portal frame air cooling support efficient and flexible steel cutting operations. Through automation, precision control, and advanced plasma technology, the RUR 3500 ensures fast, accurate, and reliable cutting of 3 mm steel plates. Metallurgical services play a vital role in keeping steel plants competitive and ready for the future. Operational support ensures that production facilities run efficiently, safely, and reliably. This includes the fast and dependable supply of high-quality spare and wear parts through a worldwide sales network, helping to avoid production delays and minimize costly downtimes. In addition, customized training programs increase the competence of employees, while experienced specialists carry out comprehensive plant upgrades. With cost-efficient modernizations and advanced mechatronic solutions, plants are maintained at the latest state-of-the-art level. Many modifications can even be performed without interrupting operations, reducing standstills to a minimum. Maintenance services are precisely tailored to ongoing production, completed quickly and with maximum accuracy. Backed by years of global experience, experts are familiar with plants and components of every design. From local repair services to full process chain support, metallurgical services provide reliable partnership, stable production conditions, and long-term productivity growth. The coke plant of the Völklinger Hütte in 1986 stood as a powerful symbol of heavy industry in Germany. As an essential part of the ironworks complex, the coking plant played a decisive role in supplying high-quality coke for blast furnace operations. At that time, the facility represented decades of technological development and industrial tradition within the Saar region. The process began with the delivery of raw coal by rail. Large quantities of selected coking coal were transported to the plant, where they were unloaded and stored in vast coal bunkers. From there, the coal was carefully blended to achieve the correct composition required for strong and efficient coke production. Conveyor systems transferred the prepared coal to the charging towers positioned above the coke oven batteries. Inside the long rows of coke ovens, the coal underwent carbonization. Each oven chamber was sealed and heated externally to temperatures of around 1,000 degrees Celsius in the absence of oxygen. During this process, volatile components were driven off, leaving behind nearly pure carbon in the form of metallurgical coke. The ovens were arranged in massive batteries, forming an imposing industrial structure that dominated the skyline of the plant. After many hours of heating, the glowing coke was pushed out of the ovens by a mechanical pusher machine. The incandescent material fell into a quenching car, which transported it to the quenching tower. There, the coke was rapidly cooled with water, producing dramatic clouds of steam that rose high above the facility. This step ensured the coke achieved the necessary mechanical strength for use in blast furnaces. In addition to coke production, the plant also recovered valuable byproducts from the gases released during carbonization. Coke oven gas was collected, cleaned, and reused as a fuel within the works. Other substances such as tar, ammonia, and benzene were extracted and processed, demonstrating the integrated efficiency of the operation. By 1986, the coke plant of Völklinger Hütte embodied both industrial power and complex engineering. Its towering structures, glowing ovens, and continuous mechanical movements illustrated the intensity of steel production in the late 20th century. Today, the preserved site serves as an industrial monument, but in 1986 it was still a living, breathing center of ironmaking, supplying the essential coke that fueled the blast furnaces and sustained the region's steel industry.